Okay, our final speaker is Sarah, who's going to give us a talk about the search for Planet 9. Sarah is a second-year graduate student and a National Science Foundation graduate research fellow. That's very prestigious, if you haven't heard of that before. And she's in the astronomy department here at Yale. Her research focuses on planets outside of our solar system that orbit suns other than our own. But she's also interested in planets that are a little bit closer to home, give or take a few light years. In her spare time, she practices yoga and she runs. Please welcome Sarah.
Hi everyone, so I'm very excited to talk to you today about Planet 9. But first I'm going to tell you a little bit about how I got here and why I became interested in astronomy. So I first became interested in math and science in my senior year of high school, when, sort of on a whim, I ended up taking an AP calculus class and fell in love with math. I was really lucky to have a very talented and dedicated teacher named Mr. Guy, yes, that's his real name, and he really showed me the fundamentals of calculus, but more than that, he really emphasized that mathematics is a tool for understanding the physical world. Everything down from atoms and molecules all the way up to distant galaxies, things on all size scales we can understand with math. And so I saw that math, which often just looks like a bunch of equations on a blackboard, can really be used to understand things like the motions of planets around a distant star. And in my first research project in college, I started to study extrasolar planets, which are planets that orbit stars other than our sun. This is called a transit light curve, and it's one of the ways that we detect planets that orbit stars other than our sun. If we monitor the brightness of a star as a function of time, and we see that there's this dip in front of it, we can infer that a planet must be orbiting that star. And the size of the dip tells you how big the planet is. And there's a bunch of other information you can get from this curve. And so my project was to try to model this curve using mathematics. And so I thought it was very interesting that we could learn this about these distant planets. And that's why I got interested in astronomy. So today I'm going to talk to you about the hunt for Planet 9, which is a hypothetical planet that is theorized to exist in the very distant parts of our own solar system. I'm going to tell you about the strong evidence for why we think Planet 9 is there, and some of the work that we've been doing to try to find it. So first let me go through a little bit of background information. So the solar system is currently composed of 8 known planets, and I thought it would be kind of a fun little test if we could say these names of these planets together. So first is Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Awesome, thank you guys, that was great. So this diagram shows the sizes of the planets to scale, but it doesn't show the separations between the planets to scale. All of these planets are orbiting around our sun, with the terrestrial planets Mercury, Venus, Earth, and Mars much closer to the sun than the giant planets Jupiter, Saturn, Uranus, and Neptune. This diagram also shows the asteroid belt, which is between, the asteroid belt, which is between the orbits of Mars and Jupiter, along with Pluto, which is considered to be a minor planet. But this diagram doesn't show one other feature of the solar system, and that is the Kuiper belt. The Kuiper belt is a disk of thousands of icy asteroid-like bodies. They hug the orbit of Neptune, extending out in a disk beyond Neptune. It's similar to the asteroid belt that's between Mars and Jupiter, except it's just a lot bigger and further out. It's thought to be a remnant of the solar system's formation, and Pluto is considered to be a member of that Kuiper belt. It's considered to be a minor planet. This is another visualization of the Kuiper belt, kind of a top-down view of the solar system. with all of these blue and orange dots being the Kuiper Belt objects, the real positions of those bodies, and the red dots here being the gas giants Jupiter, Saturn, Uranus, and Neptune. Now, the evidence for Planet 9 comes from some peculiar observations from this Kuiper Belt. So let's talk about that. In 2004, a very strange Kuiper Belt object named Sedna was discovered. Unlike most other of the Kuiper Belt objects that orbit very close to Neptune with nearly circular orbits, Sedna's orbit is extremely, extremely long and elongated and very, very far away. Even at its close approach distance, it's pretty far from the orbit of Neptune. So when Sedna was first discovered, it kind of became a mystery because it couldn't have just gotten onto this orbit all by itself. Something must have perturbed Sedna to throw it onto such a crazy orbit like this. Now, since 2004, more of these strange Kuiper Belt objects were discovered. So this diagram here is showing in red the orbit of Neptune, and all of these orbits over here are the orbits of more of these Kuiper Belt objects with very, very elongated orbits. But you also notice something else about these orbits. That is, they're kind of clustered on one side of the sky, such that if you draw lines from the sun out to the close approach distances on each one of these orbits, those lines tend to cluster to one side of the sky. And you can ask yourself, what's the chances that this clustering is just random, that we're just seeing this due to random chance? The chances are only about 0.007%, meaning it's highly unlikely that this clustering of these orbits is just due to random chance. That means there must be something that's influencing these objects to cluster in their orbits, and that influence is thought to be Planet 9. So, around a little over a year ago, two professors from Caltech, Konstantin Batygin and Mike Brown, published a paper called Evidence for a Distant Giant Planet in the Solar System, where they showed that if there was a very large planet in the distant part of our solar system, that planet could cause these objects to cluster in their orbits the way that we observe them to. Now, this paper was quite a dramatic prediction, so here they are, looking quite wistfully off into space, looking for that distant planet. And this paper got quite a lot of media attention when it first came out. You might have seen some of that media. Here's just two screenshots from the New York Times and the Washington Post saying, new evidence suggests a ninth planet lurking at the edge of the solar system. Now, Planet 9 is still a hypothesized planet. We haven't found it with the telescope yet. But there are several properties that we know about it just today without having found it yet. So let's go through some of those. Here are 9 things about Planet 9. First we know is that it's really, really big, or at least a lot bigger than Earth. It's about 10 times as massive as the Earth. That means its radius is between that of Earth and Neptune. So it would be considered to be a super-Earth or a sub-Neptune. Its interior composition would be made of ices and rocks, and its atmosphere would be hydrogen and helium, very similar to the planets Uranus and Neptune. Okay, another thing we know is that Planet 9 is very, very far away. It's about 700 times further from the sun than we are from the sun. So to give you a little sense of scale for that, here's a little animation. Here are the terrestrial planets. Then we zoom out. Here are the gas giants, Jupiter, Saturn, Uranus, and Neptune. We zoom out again. Here are those, pretty far, right? Here are these Kuiper Belt objects. They're also called trans-Neptunian objects. And then there is kind of how far Planet 9 would be. So it is pretty far out there compared to where we are relative to the solar system. It takes a really, really long time to orbit. So one trip around the sun takes about 16,000 years. One other thing we know is that it has a very eccentric or elongated orbit. So to see that, here's another diagram with these are the orbits of those Kuiper Belt objects. This little black circle is the orbit of Neptune. And then this circle here, it's actually an ellipse, is the orbit of planet 9. And you can see that its close approach distance to the sun is much closer than its far distance to the sun, and is indicating that it's a very elongated orbit. Another thing we know about planet 9 is that it affects other objects in space, kind of by definition. Planet 9's gravitational influence is what's causing these guys to cluster to one side of the sky. Okay, sixth thing we know about planet 9 is that it may have been part of the inner solar system at one time. So if planet 9 is there, the primary theory for how it got there was that it used to be one of the gas giants, just like Jupiter, Saturn, Uranus, and Neptune, but that at an early and chaotic stage of the solar system's formation, it got too close to one of these other planets and kind of got slung-shot out, vanished onto its far-out orbit. So in that sense, it kind of really is just another giant planet, just much further out. Another thing we know is that planet 9 could be the real ninth planet. So Mike Brown, one of the professors who first proposed planet 9, was actually one of the main people involved with demoting Pluto from its planethood. So really, it's only fair that he should bring another planet back into the solar system. And really, there's no question of whether planet 9 would be considered a real planet because it's so much more massive than Pluto. It's about 5,000 times more massive than Pluto. Planet 9 is going to be really dim and difficult to find with the telescope just because it is so far out there. But that is not deterring people, and the search for the planet is definitely on. So one of the main places that people are looking for planet 9 is at the Subaru telescope on top of the Mauna Kea mountain in Hawaii. This is one of the largest telescopes in the world, which is really what you need in order to find something this dim. This is just pictures of its dome where the telescope is inside. So there's a lot of dim, faint objects in the sky. So how are we going to know when we're actually looking at planet 9? So the way we find planet 9 has to do with the fact that it's going to be much closer to us than distant stars. So that if we look at the sky at two separate points in time, planet 9, because it's closer, our vantage point to it will change relative to the background stars. So if we look at it in July, it's on this part of the sky, kind of on the left side. But if we look at it again in January, it will have shifted to the other side of the sky relative to the background stars. So it's a really cool demo to look at this. And it happens by putting your finger in front of your face and imagining your finger is planet 9. Now close your eyes back and forth, and you see that your finger shifts relative to the background or background stars. If you put your finger further away from your face, the shift is smaller. And so that is the same effect that we're going to be using to try to find planet 9. Okay, but still, there's a lot of sky to search. And so one thing you can do is try to constrain where planet 9 can be in the sky. I recently made some contributions to this by writing a paper with my advisor called Constraints on Planet 9's Orbit and Sky Position. My advisor is Greg Laughlin, and we published this not too long ago. Our idea was to try to find the orbit of planet 9 that best enables these Kuiper Belt objects to maintain their clustering if we run the clock forward in time. So the idea is, if we're observing these things to cluster today, and if we assume that we're not observing them at some special moment in time, then if you run the clock forward, these guys should maintain this clustering. They need to stay relatively clustered in their orbits. So we want to consider all different possible orbits of planet 9 and find the orbit that best enables them to do that. So there are 7 different variables you have to consider if you're thinking about all the possible orbits of planet 9. There are 2 parameters related to the shape of the orbit, that being how wide the orbit is and how eccentric or elongated it is. Then there's one parameter that's the mass of Planet 9. Then there are 3 more parameters associated with how the orbit is oriented in space, kind of how tilted it is or what direction that tilt is. And then there's one parameter, that being the position of the planet in its orbit. Now we want to consider all possible combinations of these variables. And this is some of the results of that. So what I did was run many computer models using Planet 9 with different orbits and looking at what orbit best enables the Kuiper Belt objects to cluster. So all of these points are different models for Planet 9. This is showing just one of those 7 variables. This one is the eccentricity, or how oval-shaped the orbit is. On the x-axis here is a measurement of how well the Kuiper Belt objects stayed clustered. So this dashed line here is the value of their clustering at the present day. So in order for the models to match the observations, these points have to be far to the right side, meaning they stayed well clustered. Then this color bar is a measure of how well anti-aligned Planet 9's orbit was with the Kuiper Belt. Meaning, so if these guys are aligned kind of towards this side, Planet 9 anti-aligned is in that direction. So we're looking for blue points to the far right here, and so we're constraining this parameter to be around 0.4 to 0.5, or kind of a moderate eccentricity. So that's just one of the 7 variables, and if you look at that for all the variables, you have a best fit orbit for Planet 9. And this is what that best orbit looks like. So I showed this before. Here are the Kuiper Belt orbits. And then here's our best orbit for Planet 9, where the separation is evenly spaced in time. And then the coloration is according to the distance. We found that the most likely location of Planet 9 within that orbit is pretty close to its far distance from the Sun, meaning it will be that much harder to find. But this pins it down to somewhat of a location on the sky, and that is in the constellation called Cetus. So it's kind of a misnomer that astronomers know their constellations. I definitely don't know my constellations well at all. But one thing I do know is that our best fit orbit for Planet 9 fits in the Cetus constellation. So stay tuned for further observations of that part of the sky and potentially finding Planet 9 in the next couple months to years. And I want to just end with a quick little advertisement. Konstantin Batygin, who was one of the main professors who first proposed Planet 9, he's going to be visiting Yale on Saturday, April 29th, giving a public talk. And he is extremely entertaining and engaging. And so if you are looking to learn more about Planet 9, you should totally check this out. So I'll leave that up so you can take pictures of her. So thank you.
Any questions for Sarah?
Yeah.
Well, why was Pluto devoted as a planet in the first place?
Yeah, so Pluto hasn't cleared its orbit, and that's one of the main, they revised the definition of what a planet needs to do to be considered a planet. And that means there can't be debris in its orbit. And Pluto hasn't done that because it's just not massive enough. That there's all those other Kuiper Belt objects out there, they're kind of in the way of its orbit.